morning, everyone. Am I good hearable? Okay. My name is Martijn Smit. I'm Commercial Director for KELLER Pressure Sensors in Netherlands, Belgium, and South Africa. And today I will present to you a project we did at the De-Icing department of KLM Royal Dutch Airlines here in Amsterdam at Schiphol Airport. I'm waiting for the presentation. There it is. So, this is wintry conditions on an airport. Maybe you've seen when you fly in wintertime that your airplane is de-iced. Ice on an airplane is disturbing the aerodynamics. It gains extra weight. It makes an airplane very difficult to fly, or in worst conditions, almost unflyable. So de-icing is mandatory. And because it's so crucial for the daily operation of an airport, the awareness of the remaining amount of de-icing fluid is crucial. So here you see a de-icing cycle. You see here the de-icing vehicles. They are called safe arrows. You need 4 of them per airplane. A de-icing cycle takes about 15 minutes. And within 22 minutes of de-icing, the airplane must depart. Otherwise, you have to do the de-icing all over again. These are the tanks in which the de-icing fluid is stored. These tanks are pressurized. They are heated. And because they are pressurized, it makes the tank level measurement a little bit different and more complex than a classical tank level measurement. KLM consulted us in 2019 for a solution. They wanted to have a wireless measurement, so electronic measurement of the tank level and a presentation of the data in a cloud portal. We could do that. To calculate the volume of the tank, you need a few parameters, among them dimensions of the tank, the fluid density, and the actual fluid pressure. The first 2 are fixed. Dimensions of the tank and the fluid density are fixed parameters. But the fluid density, which is also known as the hydrostatic pressure, that's variable, because if you consume de-icing fluid, the level will drop. So that's the one we have to measure. We do that with a pressure sensor. The pressure sensor has to be mounted at the lowest part of the tank. But the pressure sensor not only measures the hydrostatic pressure, it measures the hydrostatic pressure plus the barometric pressure, so the air pressure, on top of the fluid. So somehow, to get the fluid pressure only, because that's the one you need for the calculation, you need to subtract the barometric pressure. You can do it 2 ways. You can use a relative pressure sensor, and a relative pressure sensor has an opening on the backside of the measuring chip. So you see here the opening. This is the diaphragm of the chip. This measures the total pressure. And due to the opening on the backside of the chip, the barometric pressure can, let's say, bounce back. So that's a mechanical way of eliminating the barometric pressure, and the fluid pressure or the hydrostatic pressure remains. Another way to do it is a differential pressure sensor. And it looks more or less the same like a relative pressure sensor, but in this case, the backside of the chip has been adapted to withstand higher pressures. And in the final end product, which you see here, you see that the backside of the chip has been converted to a full-worthy pressure port. So with a stainless steel diaphragm, it can hold higher pressures than just atmospheric pressure. And it can also measure fluids or aggressive vapors which would not be possible with a standard relative pressure sensor. This is a classic tank level measurement with a relative pressure sensor. So you have the red line here is the sensor diaphragm. You have the fluid pressure. On top of the fluid pressure, you have the barometric pressure. And those two accumulated is the total pressure. To write the formula the other way around, the fluid pressure here is the total pressure, this one minus the barometric pressure. On a pressurized tank, like we had to deal with at KLM, again, you have the fluid pressure. You have, in this case, the vapor pressure, and that can be much higher than the standard atmospheric pressure. As said, it's a vapor, so you don't know exactly what it is. And those two accumulated, again, is the total pressure. Now, in this case, we have a differential pressure, and you see on the left side of the sensor, we apply the total pressure. On the right side, we apply only the vapor pressure, and the electronic output signal of the sensor represents only the fluid pressure. And that's the one we need for the calculation, for the tank contents measurement. So these are the tanks, again, in which the fluid is stored. And here on the left side, that's the reason I recall this slide. In the yellow marking, you see a thin pipe. Maybe on the resolution of this screen, it's not very good visible, but here is a very thin pipe, and it connects to the top of the tank. So here is the vapor pressure communicating directly with one of the pressure ports of the differential pressure sensor. So you see this one. Here's the chip inside, so this is the OEM differential sensor, and we built this product of it. This is a PD33X. It has a high accuracy, 0.05% total error band. And the total error band is important because it includes all possible errors in the measurement. If you look for pressure sensors, be aware of this number, because not every company states the accuracy the same way. The definition, there's no standard for defining an accuracy in a measurement. We include every error possible, but there are also companies who only state, for example, the linearity, but not including the temperature error. And the temperature error is the worst one. In this number, we state it's all included. So it can never be worse than this number. And the second reason we took this one, it's digital. It has a RS485 Modbus output, and that makes it compatible with our LoRaWAN module. It's this one. It's called the ADT1. And the ADT1 is a LoRaWAN module we developed in our own house. It transmits the fluid level, the fluid temperature, the battery condition, the internal humidity of the device, and the barometric pressure every 15 minutes to the Things network servers. And from the TTN service, we pick the data, put it in our cloud portal, and present it to the customer. This is our cloud portal, so the only thing you need to consult the data is a browser and an internet connection. You can see it wherever you want on the world. As long as you have an internet connection and a browser, you can see these data. In this example, you see only one tank. You see here it's filled. Here they are spraying. And now it's this flat line. It means it's quiet. There's no activity. On the top of this window, there's a possibility to make tank calculations. And that's exactly what we do at KLM. Because the pressure sensor measures only the pressure in bar, but it has to be converted into a volume in liters, because that's what they want to know. What I said before, you need the fluid pressure for that calculation. That's entered here in this menu. And the cloud portal converts the data into liters. And you can see here the total volume of the tank is approximately 55,000 liters. And after spraying some airplanes, 25,000 liters is left. What important here is that you can set in the cloud portal also several alarms. On every measured channel, you can set an alarm, battery level, too high internal humidity, etc. But for KLM, the most important one is, of course, low fluid level, because that's an indication when they have to order new fluid. And here we set 3 alarms, one on 30% left, 15% fluid left, and 5%. This is the highest priority. Here they really have to order. Advantage of the ADT1 LoRa1 module. It's listed in the TTN device depository. So the registration of the device when you create a new application in the Things Network portal is very easy. And the second big advantage is in the payload, we have a JavaScript description already embedded. And that makes it very easy to implement in your system. We have very good documentation. And regarding registration of the device, this is the application portal in the Things Network. You can pick KELLER as a brand. And here are all the modules listed which support LoRaWAN. The advantages of the system as a whole, beside the known advantages of LoRaWAN technology, is that operators don't have to check the remaining amount of fluid anymore. They can focus on their main task, which is de-icing airplanes. Secondly, because of that, in wintry and slippery conditions, no one has to climb one of those tanks anymore, because that's how they did it. They climbed the tank, opened the manhole, and just have a rough estimate by looking into the tank. Now they have a very accurate measurement, and they don't have to climb that tank anymore. The icing fluid can now be ordered just in time, so not too early, and definitely not too late. And as you can see here in this picture, the de-icing fluid is sprayed on the airplane, and it flows off the airplane onto the ground. That makes it mandatory to submit environmental reports from KLM to the Environmental Council. And that's now very easy, because they have all the numbers. They see when the tank was filled, they see when it's empty, so they have the exact numbers over time, how much de-icing fluid is consumed. So a real time saver. We have 2 telemetry modules. We have the ARC1 and the ADT1. The ARC1 is the flagship, offers 10 years of battery life, supports most frequency bands around the globe. And the ADT1 is a more economical choice, nevertheless a very complete device. This is the one we used in the KLM project. It runs up to 5 years on 3 1.5-volt batteries. And both modules are compatible with every digital pressure or level sensor from KELLER. KELLER has a modular product lineup. That means we can provide you just an OEM pressure sensor, which you implement in your process. We can provide the same OEM sensor, but with a mathematical model. That means in a climate computer, we analyze the sensor on different pressures, different temperatures, and all the temperature errors caused by the sensor, every sensor has a temperature error, are stored in a database, and we give you a JSON file with every measurement we made. That makes it, together with a formula we provide as well, that you can correct the temperature error of the pressure sensor real time in your process. If that's too much engineering, we can also provide the same pressure sensor, but with electronics, and especially for IoT and LoRaWAN applications, we provide electronics which do the signal conditioning for you, the temperature compensation, and you get a very nice RS485 Modbus interface output, which you can process in your own application. Accuracy up to 0.01%. Extremely high accuracies we can achieve with this. What we do here in the microprocessor on board is in fact the same as what I showed before in the previous slide with the mathematical modeling as we call it. It's exactly the same, but now we did the electronics for you, and it's compensated real time. And at the end, we can also include the hole in a housing with a thread and a connector. And then it's called a pressure transmitter, or a differential pressure transmitter, or a level transmitter. We support a large variety of digital interfaces and protocols. We can provide you with I2C, which makes it perfect to include in a multi-parameter measuring cone, for example. We support IO-Link. We have RS485 interface with a Modbus RTU protocol. And we have sensors with a CAN-open interface. All digital pressure sensors measure the temperature as well, so you have both pressure and you have the temperature, which are very important parameters. And the digital sensors are available as well in a low energy and a low voltage version. And that makes it very suitable for field applications and battery-driven applications. We provide pressure sensors starting at 0 to 200 millibars, up to 0 to 1500 bar. It's incredible pressure. Imagine it's 1500 kilos per square centimeter. But that's possible with the latest technologies. Due to the modular product lineup, I think we can deploy a very versatile system with only a sensor, a complete pressure transmitter. The Colibri Cloud Portal I showed you is not mandatory because you can also pick the data from the TTN service yourself. If you want us to do that and store them in a database, but you have your own web interface, that's also possible because we also provide an API, and you can, with your own software, withdraw the data more or less automatically. So that's about KELLER. Thank you for your attention. And if there are any questions, I'm happy to answer them. Yeah?
To achieve the 5-year life, how frequently are you transmitting? Is it event-based or time-based?
No, it's time-based. It's one transmission per 15 minutes. For this project, that's enough. You don't need a higher frequency. The battery life also depends on the spreading factor you set in the LoRa 1 settings. I think at this project it was set to 9, SF factor 9, because laterally the distance between the measuring points and the controller's room is for about 70 meters. And what's interesting to mention here, at Schiphol Airport, frequencies are very important. You have radio traffic between the ATC and the pilots. You have frequency used by the instrument landing system. So if you roll out a system like this based on wireless data transmission, it's a no-go to interfere with the existing frequencies, which are mandatory for the daily operation of a flight. And the 868 megahertz of LoRa 1 was the perfect solution. Secondly, although 4G frequencies on of mobile phones are adapted quite well, they are still not very happy if there is a transmission source in the neighborhood of a runway. So LoRa 1 was the perfect solution here. Yeah.
Do you have any kind of alarms, like overpressure or something like this?
Sorry, can you say it again, please?
Do you have in your systems any kind of alarm like overpressure or something like this?
Yeah, what I said in the Colibri Cloud Portal, you can set an alarm on almost every parameter which is measured. For example, bad reception, that's more applicable to 4G applications, but you can set it. Too high humidity in the device, you can set. Low fluid level, of course, low battery. But you can also set an alarm on just on the pressure channel. And if you know that the standard pressure is, let's say, 5 bar, and the system detects 6 bar, you can set an alarm to that every pressure higher than 5 bars should generate an alarm. It's, the possibilities are almost infinite when it's about alarms.
Okay, thank you.
Yeah, welcome. Any more questions? Okay, thank you all for your attention.